In this video, we're going to take a look at continuous multivariable functions. So first thing we're going to do is define what we mean for a multivariable function to be continuous. Let's say that a function, we'll call it f of xy, is continuous at the point xy equal ab if the limit as xy goes to ab of our function f of xy is equal to the value f of ab. So let's draw a picture underneath this definition just to try to understand what this is saying. So we're talking about the point xy equal ab. Let's draw that on our xy axes. Let's say this is x equal a, and let's say this is y equal b. So the point xy equals ab, I would say, is right about there. Let's label that xy equals ab. Okay, and we're interested in the multivariable function f of xy. So let's draw a surface which has equation z equal f of xy. And let's just say that surface looks something like this. We'll just represent it like that. Okay, so what we're interested in here is what's happening to the values of our function f of xy near this point xy equal ab. So let's trace up to our surface here, and let's say this right here, let's label that in red. Let's say that's our value f of ab. So we could actually mark that on the z-axis there. Let's say that's f of ab. Okay, now in order for the function to be continuous at this point ab, what we need is when we're approaching this point ab from any direction, we want the value of the function to be approaching f of ab. So if we approach from this direction, we want the limit as xy goes to ab of f of xy to be f of ab. When we approach from that direction or that direction or that direction, we want to be approaching that same value. So technically, when we're talking about directions, we're talking about approaching xy equal ab in the xy plane. So we're actually imagining traveling this way, traveling that way, traveling that way. And as we go through those sequence of points approaching AB, we want the value of f of xy to be going to f of AB. But I actually like to draw us approaching the value on the surface, just because it's a little bit easier to visualize. So from any direction, as we travel along that surface and approaching the point where xy equals ab, we need to always be approaching that same value f of ab. So that's what it means for a function to be continuous at a point. And then we can extend that definition a little bit, and let's look at this second definition below the picture here. A function f of xy is continuous if it is continuous at all points xy in R2. So that's just a fancy way of saying if our function is continuous for all real values of x and y, then we just call it continuous for short. Okay, now let's look at a few typical continuous functions. Multivariable polynomials. So anything where the terms involve both x and y. So you could have something like powers of x multiplied by powers of y in each term. So x to the fourth y cubed minus 7x cubed is an example of a multivariable polynomial. We're talking about positive integer exponents on those variables, just to make it a polynomial. Also, exponential sine and cosine functions, where the argument is a polynomial in x and y. So you could have something like e to the 2x minus 3y, or sine of x squared plus y squared. So we're applying the exponential to a polynomial, to a multivariable polynomial, or we're taking sine of a multivariable polynomial. Again, those are going to be continuous functions. And then you can take sums, products, and differences of those polynomials, exponential, sine or cosine functions. So that then gives us a large class of continuous multivariable functions. And these are the types of functions that we'll consider throughout the course. Thanks for watching.